Hello, everybody. Today we're going to be writing your first quantum program, like hello world in quantum programming. But then it's not an exact hello world because you're not going to be printing out hello world, but it's going to be fun. So we just go straight into the code, and then if you're interested, you can just stay after we've written the code to learn some of the math and some of the interesting stuff behind it. Yeah, so I know you're excited to start writing the code, so let's just get into it. So the first thing that we just have to do is you have to install you have to install qiskit. So qiskit is what we're going to be using. There are two Python libraries that are usually used. One is circ, one is qiskit. Qiskit is what I'm a bit more familiar with, so I'm going to use that. I might look a bit more into circ. Qiskit is made by IBM. Circ is made by Google. So you just have to install qiskit. So I already have it installed, but yeah, it takes not too long, but it takes maybe like 5 minutes because like it installs a lot of packages. I already have everything installed. So let's just cancel that. So for some of you, you might not install immediately, so you might have to use Python 3 times tac mp install qiskit or just Python various things like that. So you can just try any of those Python tag mp install qiskit or Python 3, whatever one works for you. And so then we continue on with the actual code. All right. So just a few things. I've already kind of written out the code already. I'll just be filling it in so that it's a bit more easier for you to follow through, and then I can explain a bit more. And I don't have to type and type and type. So the first thing we have to import from qiskit. We have to import a quantum circuit because we have to build the quantum circuit. We have to build, then AER is just for actually running the simulations because we will not be running it on an actual quantum computer. There's a possibility for that with IBM quantum computers back at IBM headquarters, and then they execute to actually execute the simulation. Then we create a quantum circuit. So what we're doing here is actually creating a quantum circuit, which would be represented. We can represent it as a matrix. We can represent it. I think I might just show a picture there. We can also represent it as like kind of like a diagram. There's a way it's drawn. I can't remember the exact name for the quantum circuit diagram. I was thinking of QCD, quantum circuit diagram, but that's quantum chromodynamics, which I actually don't know what it means, anyways. So we see here that we're just creating a class, and then the first two just represents the qubit registers. So and then the second to represent the classical registers. So these two represents so the zero and ones. Essentially, they are basically two states that can be zeros or ones, and then these last two essentially represents the classical states because even though we're dealing with quantum mechanics and the world is quantum in its reality, but then we still have to bring this result back into the classical world. That is the normal state of things. If we are unable to read those results, we can't read those results while they're in quantum state. We have to bring them back into classical state. So then we apply the Adamat gate. I'm going to explain this a bit more in the later part, but essentially this is what we're used to apply superposition. Then we have the control NOT gate. In this case, what we're trying to do is we're trying to match, not match, but like we're trying to entangle. Yeah, that's the right word, quantum entanglement. We're trying to entangle these two states. So we have the first one being the control register, and then the second one being the target register. It's the idea of dependent and independent variable. I also explained that in the other part of the video where I'm going to explain everything. Then we just measure everything, and then now comes the part where we actually simulate. So this is where AER is important. We're just essentially getting the back end. So we're using the simulator here. We're not actually running it on actual quantum computers, and then we execute it on the simulator, and then simply we just get the result. We after the job has been executed, we get the results, and then we count them, and then we print the count. So let's just run this. So that will be Python 3 qc.py, and so this will just run very quickly actually and give us results. We're waiting. Okay, so we have results. So these are essentially our results. So we have 00496, and so the essential interpretation of this result is these first two ones represent the quantum registers, and the second one represents the classical registers. So the idea is that it is in a state, it can either be in a state of 0, 0 or in a state of 1, 1. So 0, 0 or 1, 1. These are the states that it can be in. And then there's a 50-50% chance. You can see that these are very close. This is essentially 500, 500. If you didn't notice, we are running about 100 shots, 100 kind of like 100 iterations. So that's why these numbers add up to, oh my, took away my, I think it took away my, all right. So that's why these numbers add up to 1,000. So the quantum registers, the classical registers. So these classical registers just measure the values. So we have our quantum registers. Of course, it's not necessary to put it here because it still kind of gives us exactly what we need. So we could just have removed this, the second two over here. So this is basically an hello world program in quantum programming. So we've run the program on a simulated backend, and we've actually gotten it back now. There's a 50% chance. I don't know why but I know that it can't be 0, 1 or 0 or 1, 0. So like it can be, let me just put this here. It can be 0, 0. It can be 0, 0, 0. It can be 1, 1, but not 1, 0 or 0, 1. I don't know exactly why. I'm still learning this. I'm going to get into more of learning it, and I'm going to teach you more of it as I learn it. So just go to the next part of the video now and just watch a bit more explanations on some of these functions. Not functions now, but they are kind of quantum gates. Like the H is the Adamat gate, CX is the control NOT gate, and so like that. All right. See you in the next section. All right, so that coding part might not have been as exciting as you wanted it to be, but we can just learn some of the math and physics behind it. And so the basic idea with quantum programming is that, in difference to classical programming, we don't use bits, but we use qubits. So a bit is essentially a number that is binary that can be either in a state of 0 or a state of 1. But the idea of qubits is that quantum mechanics are now brought into the whole thing. So we can have entanglement, which we saw with the control NOT gate. We can have superposition, which we also saw with the Adamat gate. So these are some of the things that we'll just look into very briefly, actually. So one of the things that we see with qubits, one of the ways that we can form qubits is that, so let me just illustrate a bit here. So one of the ideas with qubits is that the qubit can either be completely zero. Let me change this color to something much more beautiful, I guess. Let's use yellow. All right. So it can be completely zero, or it can be completely 1. And it can also be any linear combination of these two. So basically, we're treating them like vectors in linear algebra here. And linear algebra is something that is very important. I just posted on Twitter a while back that I realized that many of the operators and gates were actually matrices. And so linear algebra was a very big thing in quantum mechanics and quantum programming. So a linear combination. So essentially, a linear combination is the idea of multiplying each of these vectors. Let's just think about them as vectors now. Let's say these arrows point towards particular vectors. So it's the idea of multiplying each of those vectors. So let's say this is a vector a vector X, and this is a vector Y. So the idea of a linear combination now is multiplying each of them by a constant. So that would be multiplication by a constant A and B for X and Y. That would give us a linear combination. That's the essential idea of a linear combination, and that would give us another qubit. And so these are the ideas of linear combination of atomic orbitals, superposition, and the like. So this is it's this linear combination from which we begin to get things like superposition. And then we see a lot with entanglement, which we saw with the control NOT gate. So the idea of the control NOT gate is that it links the target and the source registers, essentially the control register. It links them together in such a way that their states are very much correlated to one another. So that one state affects the other. It's kind of like the idea of dependent and independent variables in statistics. So y being the dependent variable and x being the independent variable. It's not related to what we're talking about here exactly, but then it means that their values are very much correlated. So yeah, a change in one state causes a change in another state. So that's that essentially. And so um, so the next thing is I just wanted to show you these two matrices essentially. So this matrix essentially is what represents. I say essentially a lot. Maybe I should move. I should put an essentially counter. This is the control knot matrix, the one that helps us cause entanglement within the registers. And then this is the Adamant gate that we were seeing. So these are just the matrices that represent them. So we can see that whenever we are applying the Adamant gate or the control knot gate, we're seeing that what we are doing is actually performing matrix operations. But from a bit of my research, I found out that it's not exactly the same way. It seems to be a chronicle product. It will be actually very funny if a chronicle product is the same as matrix multiplication, but I don't think it's the same because I remember the idea of a chronicle delta from tensor calculus. But then let's just leave that for now. I hope you've learned some amazing things today with linear combinations being essentially, so this is essentially superposition. And then you've learned about control knot gates, which help us to cause entanglement by correlating the states of two qubits such that once the change in one state affects the other one, and then an Adamant gate which helps us achieve linear combination or superposition, which is essentially this. So the Adamant gate and this linear combination are very much linked. Thank you very much for watching.